Hi class, welcome back to our continuation of lectures on quantum mechanics, and it's the third series of the sixth chapter. And again, our main reference is Introduction to Quantum Mechanics by David J. Griffiths, and I recommend you to buy this book once again. So to start with, we will be considering the ZMan effect. This is another perturbation that's going on in an atom. So the ZMan effect occurs when an atom is placed in an external magnetic field. So you have a BEXT. The energy levels of the atoms are shifted, and you will be having the generate states being shifted to discrete states. So for a single electron, the perturbation is given by these. So there are two components of magnetic dipole moment. You have magnetic dipole moment associated with the electron spin, and the dipole moment associated with the orbital motion here. As you can see, S and L are actually related to each other. They sum up into one total angular momentum, but let's see it later. And as you can see, equation 6.68 is just 2 times as equation 6.69. So if you rewrite the Hamiltonian, you will have this. The Zeeman splitting of orbitals actually depends on the how strong is the external magnetic field. So if it's stronger or if it is weaker than the spin orbit coupling, which we have studied in the previous lecture. So if the external magnetic field is much less than the internal magnetic field, then the fine structure correction will dominate, and as Hz can be treated as a small perturbation. But if the internal magnetic field is much smaller than the external one, then the Zeeman effect will dominate, and the fine structure becomes the perturbation. So there are 3 cases that are considered here, including the intermediate zone, where the external magnetic field and the internal magnetic field are comparable to each other. And in this zone, degenerate perturbation theory must be used, and diagonalization of a relevant portion of the Hamiltonian would have to be done by hand. So we have 3 cases here where the external magnetic field is much smaller, and here where the external magnetic field is much larger, and the intermediate zone. So let's start with the weak field ZMan effect. It's when the external magnetic field is much smaller than the internal magnetic field. So here in this particular scenario, the fine structure dominates the situation, and the good quantum numbers are n, as we have been as we have studied in the previous lecture. The good quantum numbers here are n, l, j, and mj, but not ml and ms, because in the presence of spin orbit coupling, L and S are not separately conserved. In the first order perturbation theory, the ZMan correction to the energy would have to be written like this, and that you can also review in the previous lecture. But here we note that J is equal to L plus S, so your L plus 2S would have to be J plus S. But unfortunately here you have to get the expectation value of S as well, because of this one here, because of the extra S. The total angular momentum is actually just J is equal to L plus S, but L and S precess rapidly about a fixed vector J, so here your L could change its value and your S could change also its value, but they have to have a total sum of J. So this one here is a constant, and here you could have a smaller L and a larger S, for example. It depends, for as long as the J is or the total angular momentum is constant. But the time average value of S is just actually the projection of S along J. Well, there's nothing wrong about using the average value of S. So as you can see from here, S dot J is a scalar, and so if you project it in the vector J, then you have to multiply it with J, and of course you have to divide it by J square in order that you will just have an S, the value of S. So here you have L equals J minus S, and so your L square will have to be this. And using the eigenvalues of these vectors, so for J square you have H bar J times J plus 1. For S you have this, and for L you have L times L plus 1. And so it follows that this one here would be written in this form. By the way, the term in the square bracket is known as the Landi G factor. This one here. That's the Landi G factor. Choosing the z-axis to lie along the external magnetic field, then our correction to the first first correction would have to be this one. Where the Bohr magneton is equal to this. That's here. Now the total energy is the sum of the fine structure part, which is equation 6.66. If we could just go back. Here in the previous lecture, this one here, this is the correction of the fine structure, I mean related associated correction from a fine structure constant. And so again, the total energy is the sum of the fine structure part, which were studied earlier, and the ZMan contribution. As you can see, for for n equals 1, L equal to 0, and J equals 1/2, so you have a ln G factor of 2, and this one will split into two levels. The energy for n equals 1, L equals 0, J equals 1/2. This will split into two because the mu b here will have a term that has mj equals 1/2 and mj equals -1/2. So it will split into two, and the graph for that would have to look like this. So that's the weak ZMan splitting for ground state. The upper line is mj equals 1/2 and has a slope of 1, and the lower line is mj equals -1/2 and has a slope of -1. By the way, if you have time, you can solve also this problem. 6.19. So you can understand more about the topic. Now the next case is the strong field ZMan effect. So if the external magnetic field is much stronger than the internal magnetic field, the effect is known as the Bastian-Bach effect, or the strong field ZMan effect. And with the external magnetic field in the z direction, the good quantum numbers here are n, l, ml, and mz, and not j and mj, because in the presence of external torque, the total momentum is not conserved, while LZ and SZ are conserved. So the ZMan Hamiltonian here is written in this form instead of the total L and the total Z. And of course, the unperturbed energies would have to be this one. In the first order perturbation theory, the fine structure correction to these levels is calculated by this one here. The relativistic contribution is the same previously, and the spin term, going back to equation 6.60, requires that Sx equals Sy equals Lx equals Ly to be 0 for eigenstates of Z and Lc, because they're the ones constant in this case. I mean, not constant but conserved. So your S dot L would have to be just this term, and this one here is the expectation value of the dot product of S and L. And if we go to problem 6.20, we'll be able to find, by doing this comprehensively, we will be able to get the first fine structure energy correction will have to be given by this. This one. So the term here, this term, this one, is indeterminate for L equals 0, and so in the case where L equals 0, the value of that in that region is just equal to 1. And to explore more on that, you can solve 6.22, so that to convince yourself that the value in that square bracket is 1. You can also solve 6.21 if you have time. So now we'll go to the intermediate zone, where the external magnetic field and the internal magnetic field are about the same magnitude. So in that regime, neither Hz prime nor the H of the Hamiltonian of the fine structure dominates. So they must be treated in the same footing as perturbations to the Bohr Hamiltonian, and so your total perturbation would have to be given by this. For the case n equals 2, we can choose as the basis for degenerate perturbation theory the states characterized by L, J, and Mj, but L, ML, and MS can also be used, but this one here, this one makes the matrix elements of Hz easier, but those of HFS more difficult. But its eigenvalues are the same, either this, you use this, or this one. So we can use this, or we can also use that. If we use this will be more difficult to work with. This is easy. And if we use this one here, this would be easy. This would be easy, and this one would be difficult here. So anyway, that's the take there. So you either choose the states characterized by L, J, and Mj, or L, Mj, NMS, and then you can do it in two ways, but then you're supposed to get to the same, approximately the same result. Using the Klebsch-Gordon coefficient, we can go back to problem 4.45, or you can see table 4.7, and we can relate these quantum numbers to the linear combinations of LMJ and SMS, so that you can relate these ones here, these ones, and this one. So you have this for L equal to 0, and you have for L equal to 1. You can just look at the ket spin states in ket. So in this basis, the non-zero matrix elements of H fine structure perturbation are all on the diagonal, and given by the equation 6.65. You can go back to the previous lecture for this, and HZ prime has 4 off-diagonal elements, and the complete matrix W, if we would have solved the problem 6.23, would be given by this. We will be able to achieve this matrix. So you have an 8 by 8 matrix, where here gamma is just alpha over 8 square times 13.6 eV, and beta is just the Bohr magneton times the external magnetic field. The first 4 eigenvalues are displayed along the diagonal, as you can see in the matrix here. So these are already the eigenvalues. You don't have to get the characteristic equation of this part here. You have only to get the characteristic equation here, so that you'll be able to diagonalize the matrix, and also this part here. So the characteristic equation for the first one, this one, would have to be this, and it will give you eigenvalues equal to this one here. But also the eigenvalues of the second block would have to be the same, but with the sign of beta reversed. So we can have the 8 energies if we were able to diagonalize the matrix. The 8 energies would have to be given by this one, this one, this one, this one, and the eigenvalues here and here. So that would be the energy levels for N2 states of hydrogen. We have fine structure plus ZMan splitting. So the 4 diagonals here, and then the eigenvalues of the next 2 4x4 blocks in the mother matrix. In the zero field limit, where the beta is equal to 0, they reduce the fine structure values. For weak fields where beta is very much less than the gamma, you can solve 6.19. Sorry, this is gamma, not y. So solving problem 6.19 would give you a result for weak fields where b is equated to 0, and then for problem 21, that's for strong fields where the beta is very much less, very much greater than gamma. So these are the 8 energy states for N2 of the hydrogen. N equals 2 for the hydrogen electron. So if you would be able to see the graph of the 8 energy states here, 1 2 3 4 5 6 7 8, and you have here some two of the energies they have almost the same value. So the strong and the weak would have splittings here in this part here, and in this part, in this 1 2 3 and 4. And for the intermediate state, for the intermediate zone where the internal and external magnetic field are comparable, you will have the splittings here in this region here. So if you have some time, you can solve these problems 6.23 and 6.24. Now we'll go to the hyperfine splitting. The proton also constitutes a magnetic dipole, though its dipole moment is smaller than that of the electron because of the mass of the electron here is so much bigger, so much smaller. So in that case, the dipole moment of the electron would have to be, magnetic dipole moment of the electron would have to be larger than the proton. And the proton is also a composite structure, and that means it's made up of some tinier particles. And as we have known, it is made up of 3 quarks, and its gyro-magnetic ratio is not as simple as the electron, and its measured Lagrange G factor is 5.59 as opposed to the electron, which has only 2. The Lagrange G factor in equation 6.74, if you could go back, plays a similar role in the proportionality between the electron's total magnetic field, total magnetic moment, which is mu L plus mu S, and its total angular momentum J. So according to classical electrodynamics, if you could remember your lectures also in that subject, a dipole mu sets up a magnetic field. So you will have a magnetic field like this. So the Hamiltonian equation 6.57 of the electron in the magnetic field due to the proton's magnetic dipole moment is therefore given by this one, which is now the Hamiltonian perturbation, perturbation of the Hamiltonian due to the hypersplitting hyperfine splitting is given by this. According to the perturbation theory, the first order correction to the energy is the expectation value of the perturbing Hamiltonian, which is this one here, where phi sub O square given by this. In the ground state or any other state for which L equals 0, the wave function is spherically symmetrical and the first expectation value vanishes. And you can see this result in if you could solve problem 0.625, but for now just accept it. So meanwhile, from equation 4.80 for the hydrogen atom, phi 100 of 0 square, or the square of the probability density. By the way, this is phi 1000 0 square is equal to 1 over pi a cube, and so that your correction of the hyperfine splitting would be given by this in the ground state. This is called the spin-spin coupling, which involves the spin of the proton and the electron. Now, in the presence of the spin-spin coupling, the individual spin angular momenta are no longer conserved. And now the good states are the eigenvectors of the total spin, which is equal to this. And so if you square that, gives you the dot product of S and SP and SE, which is equal to that. But then again, you have two fermions, two spin 1/2 particles, so SE square and SP square would have to be 3/4 h bar square. In the triplet state, parallel spins, the total spin in the triplet state, the parallel spins has a total of 1, and hence your S square would have to be 2 h bar square. And in the singlet state, the total spin is 0 and S square is equal to 0. Thus, your first order correction due to the hyperfine splitting is this, given by this one. So you will have for the triplet states 1/4, and for the singlet state would have to be -3/4, so that the spin-spin coupling breaks the spin degeneracy of the ground state, lifting the triplet configuration and putting the singlet configuration down below, and putting an energy gap between the singlet and the triplet, which is delta E here. This is the hyperfine splitting in the ground state of hydrogen. So the energy gap here, if you would be able to know the values of these quantities of these of the terms here, that would be 5.88 times 10 to the negative 6 electron volts. So the frequency of the photon emitted in a transition from triplet to singlet state would have to be given by this. And of course, the corresponding wavelength for this particular frequency is 21 centimeters, or this is the microwave region, and this is called the famous 21 centimeter line, and is among the most pervasive and ubiquitous forms of radiation in the universe. So you have this microwave region. It's very common in the telecommunication system. So these are the problems that you have to experience solving. It doesn't matter if you finish one problem, for as long as you know how to start start the solution and be able to sketch the solution, it would be fine. So I will just show them to you slide by slide. You can take a screenshot, and then, well, if you review the videos, then you would probably have the idea to know how to solve these problems. So this ends the chapter, and stay tuned for the next one.